Hello everyone, welcome back. In this particular video, we're going to start a discussion on Swern oxidation, which is another reagent that's used for the oxidation of alcohols. Now, Swern oxidation is also a selective oxidation for primary alcohols because primary alcohols can be selectively oxidized to aldehydes. There is no over-oxidation to the carboxylic acid. Secondary alcohols are converted into the corresponding ketone. Now, I've captured a general reaction here. The reaction itself is done in two steps, and I'm using the example of a secondary alcohol here. So a secondary alcohol is converted into a ketone. So the reaction, like I said, is done in two steps. The first step is the reaction of the secondary alcohol with Dmso and oxalyl chloride. Dmso is dimethyl sulfoxide. This is the structure of Dmso, and we can actually write a resonance form for Dmso. Okay, so this oxygen here has 2 lone pairs, and this one here has 3 lone pairs. All we are doing is pushing that arrow up. So we can actually write a resonance form for it. And that's the resonance form that we're going to be using in the mechanism of this reaction. Oxalyl chloride, COCl2, has a structure like this. So this is an acid chloride, in fact, a diacid dichloride, okay? Or the acid chloride of a dicarboxylic acid. So the first step is the reaction of the alcohol with Dmso and oxalyl chloride, which generates an intermediate. And in the second step, that intermediate is treated with a base, triethylamine. So triethylamine, this behaves as a base, but it's a very specific base that's used for this reaction. So you cannot put like sodium hydroxide in this system, okay? So this is an organic base, triethylamine, that's used. And so when you do this, secondary alcohols would be converted into ketones. If you're working with a primary alcohol, that would be converted into the corresponding aldehyde. Let's look at the mechanism of this reaction. What is the mechanism? How do all of these reagents come together to give us a ketone product? Okay, and like I mentioned, the reaction has 2 steps. The first step is the formation of an intermediate, which then reacts with the base. So we start off by the reaction of our alcohol, not the alcohol, the Dmso with the oxalyl chloride. Okay, so if we start with Dmso, and like I said, we're going to use this resonance form of Dmso. The Dmso reacts with oxalyl chloride. So this oxygen is nucleophilic here. So this oxygen can go and attack this acyl carbon because that's going to have a del positive on it. So the oxygen goes and attacks this acyl carbon. When that happens, the first step is for this oxygen to get pushed up, the double bond to get pushed up to the oxygen, okay, which generates an intermediate where we have an O minus Cl. We have C double bond O Cl, and our Dmso is now connected to that oxalyl chloride. In the second step, this double bond or the lone pair comes back to form a double bond, and simultaneously a chlorine or the chloride gets kicked out. Okay. This is now going to give us a new intermediate where we have the carbon, double bond O, is connected to the C double bond and Cl, and plus we have a Cl minus that was kicked out. Now this chloride can come and do an attack on this sulfur, and when it does that, simultaneously this oxygen leaves, okay? And when that oxygen leaves, it forms a pi bond here. And simultaneously, there are a few steps that happen. Okay, so that double bond forms. Simultaneously, this comes to the carbon and the oxygen, and the chloride gets kicked out. Okay, so by the end of this, what we've done is we've generated an intermediate where we have a sulfur with two methyl groups, and there is a chlorine connected to it. The sulfur still has its positive charge to it. Okay, and plus we've created or we've generated carbon dioxide, that carbon with the two oxygens, double bonds to both oxygens, carbon dioxide, plus carbon monoxide, carbon with the oxygen. There's a triple bond, formal triple bond over there, and a chloride ion. This intermediate that we've created, this is the chloro dimethyl sulfonium ion. That's our active intermediate, which then undergoes the oxidation, or that helps the oxidation of the alcohol. So once we've generated this chlorodimethyl sulfonium intermediate, this is when our alcohol comes in. Okay, so the alcohol comes in. That chlorodimethyl sulfonium intermediate is now attacked by the alcohol. So the alcohol can go and attack the sulfur, and the chlorine would get kicked out, such that we're going to create a new intermediate where that sulfur is positively charged, and we have the oxygen from the alcohol connected to it, and this oxygen would have a positive formal charge to it. And now the base triethylamine, this kicks in. So we are doing the second step now here. The base kicks in, and it will deprotonate this intermediate to give us a sulfur with the oxygen and the alcohol now connected to that sulfur atom. Now, if we notice, now we are really close to making the ketone product, because all we have to do is we have to remove this alpha hydrogen and put a double bond between the alpha carbon, or the carbon here, and the oxygen to give us the carbon oxygen double bond. Okay, so we are really close to the end product here. So one of the possibilities from here, or one possibility for the mechanism from this step here, is that the base deprotonates the alpha hydrogen, which simultaneously forms a double bond with that carbon oxygen, okay, or double bond between the carbon and the oxygen, and the electrons from here go back to the sulfur. And that would give us the ketone product. Okay, we've got the carbon oxygen double bond now, plus it's going to give us the sulfur with the two methyls to it, which is our dimethyl sulfide. That's one of the byproducts that's formed in this reaction. Now, another school of thought, or another possibility here, which I'm going to show here, is that the base, instead of deprotonating this alpha hydrogen, instead of deprotonating the alpha hydrogen, the base here in this particular step it could deprotonate one of the hydrogens in this methyl group. Okay, because that methyl group is next to the sulfur with a positive charge on it, these hydrogens are going to be relatively acidic because once you make the conjugate base, that can be stabilized by resonance. Okay, so that's going to make them, render them acidic. So the base can deprotonate this, this hydrogen, one of the methyl hydrogens, and this will give us an intermediate where, let me draw this a little bit correctly here. So this would give us an intermediate where we have the sulfur with a positive charge to it, and we will have one of the methyl groups with a negative charge to it, and we have the oxygen, we have the alcohol that's connected to it with the alpha hydrogen here. So the other school of thought, unlike what we saw earlier, is that this negative charge can do an intramolecular or intramolecular deprotonation. So that can deprotonate this hydrogen instead of the base deprotonating it. It can deprotonate this alpha hydrogen, and the electrons can go here, and that would put the electrons back. And that electron push would again bring us to the same products here. So this is in contrast to what we did earlier, where the base deprotonated the hydrogen. So we looked at two possibilities. One was that the base could deprotonate that hydrogen. Electrons from here could go there, and that could happen, and that would also bring us here. But those are two schools of thought, the two proposed mechanisms for this reaction to happen. But in the end, essentially, we convert that secondary alcohol into the ketone, and now if you track down all the products or all the side products that are formed, what we've made is we've made carbon dioxide, we've made carbon monoxide, we've made chloride, and plus we've made dimethyl sulfide. So one of the advantages of the Swern oxidation reaction is that all of these side products, except for the chloride, okay, so most of these side products are volatile compounds. That means they are gases. So then when you do this reaction, if your reaction goes completely, you can cleanly convert your secondary alcohol or your alcohol into the ketone product. Again, just to reiterate, I use the example of a secondary alcohol to walk you through the mechanism, but this oxidation reaction can be applied to both primary alcohols and secondary alcohols.